Invalid resource data is the primary cause of integration failure in health tech ecosystems. A resource conforming to the base specification is insufficient. It must adhere to local implementation guides defined by custom profiles. We are implementing rigorous structural and semantic validation, not basic schema checks. The core challenge is ensuring that mandatory elements defined in your structure definition, like specific identifiers or required extensions, are present and correctly formatted. If a patient resource lacks the required local patient ID extension defined in your custom profile, downstream systems cannot process it. This validation step must occur immediately upon ingestion or creation, preventing data pollution before persistence. We will detail the exact steps to load and apply these complex constraints using established validation engines. A structure definition is the blueprint for validation, defining constraints beyond the base FHIR specification. Key components are the differential and snapshot elements. The differential specifies changes relative to the base resource, while the snapshot provides the complete view. Focus on the element definition within the differential. This is where cardinality, data types, and binding strength are enforced. For instance, setting minimum equals 1 on an element makes it mandatory within your profile context, overriding the base specification's minimum equals 0. Understanding the path attribute is crucial. It maps directly to the resource element being constrained, such as patient.identifier or observation.valueQuantity. We must programmatically parse these definitions to build the validation rule set. Effective validation requires a dedicated engine, typically leveraging libraries like FHIR Validator or the official reference implementation validator. First, the engine must be initialized with all relevant structure definitions, including the base FHIR definitions and all custom profiles. This involves loading the definitions into a validation context or registry. The process involves reading the structure definition JSON or XML files and registering them using the iWorker context interface. When a resource arrives, the engine identifies the target profile, usually via the resource.meta.profile element. If multiple profiles are asserted, the resource must pass validation against all of them simultaneously. Cardinality validation is the most frequent failure point. The validator checks if the number of occurrences of an element falls within the minimum and maximum bounds specified in the element definition. If your profile mandates a specific identifier system, the validator checks the identifier list. It verifies that at least one identifier exists where the system matches the required uniform resource identifier defined in the profile slicing discriminator. If minimum equals 1 and the element is absent, the validation fails immediately, generating an OperationOutcome resource detailing the missing path. This is not merely checking for null, it ensures the presence of structurally required data points. Slicing allows constraining repeating elements based on specific criteria, ensuring only defined subsets are used. The validator must first identify the slicing discriminator, often based on a fixed value in a sub-element, like the system uniform resource identifier for an identifier. It then checks that every instance of the repeating element conforms to one of the defined slices. Custom extensions, defined by their own structure definition, are validated against their specific constraints, including their value type and cardinality. The extension uniform resource identifier must match the definition, and the contained value must adhere to the specified data type, such as code or quantity.
Terminology binding ensures coded elements use values from approved value sets. The element definition specifies the binding strength, required, extensible, preferred, or example. For required bindings, the code must exist within the referenced value set. The validation engine performs a terminology lookup against the configured terminology service. If the code system is external, the service must be accessible and synchronized. If the binding is extensible, the validator checks if the code is conceptually appropriate, but strict membership is not mandatory, though a warning is typically issued if the code is not found. System analysts must configure the validator with the correct value set expansion mechanism. FHIR Path provides a powerful expression language for defining complex cross-element constraints that standard cardinality checks cannot handle. These constraints are specified in the element definition.constraint array using the expression attribute. For example, ensuring that if observation.status is final, then observation.effectiveDateTime must be present. The validator executes this FHIR Path expression against the resource instance. If the expression evaluates to false, the constraint is violated. Implementing this requires a robust FHIR Path engine integrated into the validation framework. capable of handling functions like exists, where, and all. Some constraints, particularly those involving business logic or external system state, cannot be expressed purely in structure definitions or FHIR Path. These require custom validation code hooks. The validation framework must allow registration of custom validators that execute after standard structural checks. Instance, verifying that a referenced practitioner resource exists in the database, or checking a checksum against an external registry. These custom validators receive the resource context and return operation outcome issues if the external business rule is violated. This ensures end-to-end data integrity beyond schema conformance. The output of any validation process is an operation outcome resource. This resource contains a list of issues, each detailing the severity, code, location, and diagnostic message. Severity levels include fatal, error, warning, and information. System analysts must configure the application to treat error and fatal issues as rejection criteria. The location element, often expressed as a FHIR path, pinpoints the exact failing element within the resource, enabling precise feedback to the data source or user interface. Parsing the operation outcome efficiently is critical for automated error handling and debugging. Validation must be integrated into the continuous integration and continuous deployment pipeline, ensuring that profiles themselves are valid before deployment. At runtime, validation should occur immediately post-data ingestion, before persistence to the primary data store. Implement a dedicated validation service endpoint that accepts resources and returns the operation outcome synchronously. This prevents invalid data from ever entering the system. For high-throughput environments, consider asynchronous validation queues for non-critical warnings, but mandatory constraints must be checked synchronously at the transaction boundary. This proactive approach minimizes downstream data quality issues.